I want to thank the organizers for inviting me to give this talk. Again, my name is Bryan Baxter. I'm from the University of Minnesota, and I'm presenting work done with my colleagues on combining high-definition transcranial direct current stimulation with sensorimotor rhythm-based BCIs. So, with that, we all know the promise of these BCI technologies and the goal recording some type of brain signal, processing it, classifying it, and allowing the user to control something in the environment, be it a robotic arm, a quadcopter, a speller. And in particular, what we're using is sensorimotor rhythm BCIs using EEGs, or using EEG. And there's multiple obstacles with this, so you have things like lengthy training times, tiring motor imagery tasks, so people doing this can only do it for maybe an hour at a time, and the difficulty with some subjects in actually learning to control, to self-modulate sensorimotor rhythms. So our approach is to use a non-invasive neuromodulation technique to try to beneficially affect the self-modulation of sensorimotor rhythms. So to do this, we're using transcranial direct current stimulation. So with that, we have multiple electrodes set up, set up on the scalp, where we're stimulating a particular area of the brain. So here we have a high-definition setup with one center electrode and 4 surround, localizing the stimulation to the sensorimotor cortex. Generally, anodal stimulation is thought of as excitatory, and cathodal is thought of as inhibitory. This is in TMS studies looking at motor evoked potentials. So there have been many studies looking at motor learning, and they found that pretty conclusively that anodal stimulation prior to or during motor learning will improve that motor learning. The studies with motor imagination and BCI is a little more mixed. So some groups have found no change in performance, but a change in electrophysiology. And other groups haven't really found a change in performance or electrophysiology. So we wanted to look at this a bit more in depth and actually stimulate while people are doing the BCI, which hadn't been done before, to see if we can beneficially improve performance. So we hypothesized that simultaneous TDCS with sensorimotor rhythm-based BCI will improve performance and possibly learning. So we have our experimental design set up right here. We have an illustration of the cap here with embedded electrodes. So we have the central electrode located between C3 and CP3 here, and the return electrode opposite polarity are located between adjacent EEG electrodes. This allows us to stimulate and record at the same time, getting a signal from most of the adjacent EEG electrodes, though occasionally we do have to remove some of those electrodes. On the upper left, you can see the actual experimental setup. So the subjects come in, they do C2 right-left trials prior to stimulation. And then we do 20 minutes of 2 milliamp TDCS stimulation while they also do the motor imagination trials. So they do about 90 to 108 trials in this stimulation time period. After we turn off stimulation, then we immediately start them back up doing these BCI trials. We call this the immediate post-stimulation time block. Then we have them do 13 minutes of a visual oddball task. That's to keep them engaged, sitting there, but give them a little break from doing the motor imagination. And then finally, we have them do another 72 trials of the BCI task. We call this the delayed post-stim time point. So we have 4 blocks of BCI trials within each session that we get data. And the subjects have 6 seconds for each trial to acquire the target. And acquiring the target consists of moving the red ball to the yellow target, either to the left-hand side or the right-hand side, by imagining opening and closing either the right or the left hand. So we had 29 healthy subjects come in. They were randomized into 3 groups. Each person came in for 3 sessions, and they got the same type of stimulation each session. So if you were assigned to the anodal group, you came in for 3 sessions and got anodal stimulation during each session. The task setup was using the BCI 2000 cursor task, which perhaps you could tell from the illustration, with C3, C4 control, and 11 to 13 hertz autoregressive power was used input into the classifier. So with that, we can get to the results. So I'm going to go over the layout here because my next couple of slides are laid out similarly. I'm actually going to I can't. Okay. So the orange group is the cathodal group you can see over here. So the orange is cathodal group. The teal or light blue is the anodal group. Hopefully you can make that out. The gray is the sham group. These are standard error bars. And on the right side, on your right, you have the right-hand trials, and then left-hand imagination trials. Across the x-axis, we have time point. So session 1 pre-stim, that's their initial time point. And then this is going to the session 3, their delayed post-stim block here. So this is basically all the data we have for this specific measure, which is % valid correct. And this is actually baseline subtracted. There was a significant difference at the beginning between the anode and the cathode group. The anode was slightly better. So we baseline subtracted so we could see the trajectory for all the groups. And basically we see these groups, there was not a significant learning over time, and there really wasn't a difference between the groups for this % valid correct measure. However, that changes when we look at the time to hit correct target. So this is another measure of performance. And left-hand trials, there's no difference, but for the right-hand trials, there is a difference. You actually see that the anode group is faster than the cathode group at acquiring targets. This is significant over time, and what we want to do with this is say, okay, that's interesting over time that this happens. What happens within a particular session when we're actually stimulating? So here we collapsed across sessions and just see the time blocks. So pre-stimulation, during stim, immediately post, and delayed post. And again, this is normalized to the pre-stimulation time point. There was actually no difference, but it's kind of easier to see the trajectory when we normalize. And again, the left-hand trials, there's no difference. Right-hand trials, you do see the anode after stimulation gets faster. So it's significant between the anode group and the sham group at this delayed time point, and the anode group and the cathode group. You start to see the trend at this immediately post-stim. That's not significant as of yet. And if you actually look at the raw values down at the bottom, you see that the anode group decreased about 600 milliseconds from the pre-stimulation to the delayed post-stimulation time points. So starting at 3.3 seconds and dropping down to about 2.7 seconds. So that's a pretty significant decrease. So with that, then we can move on to electrophysiology. So this is the alpha power across kind of the sensorimotor strip here. And this is normalized to the pre-stimulation baseline again. This is just kind of to give you a general qualitative sense of what was going on. So blue is an increase in alpha power, yellow is a decrease in alpha power. You have the anode group, cathode. And what you can see is for both right and left-hand trials, you see kind of an increase in alpha power over time for the anode and the sham group. What you don't see is this increase over time for the cathode group, particularly over the stimulating electrodes. So we thought that was pretty interesting to see, and it wasn't necessarily expected. But we wanted to quantify it more, so we looked at specific electrodes. So here we're looking at specifically the C3 electrode. The results are similar for CP3 as well. And again, what you see is for right-handed trials, there's a difference in alpha power between a sham and the cathode, and an anode and the cathode for right-hand trials post-stimulation. So there's a trend for the left-hand trials. If you look at this, this is not significant as of yet, but there's a trend towards it there. So in conclusion, high-definition transcranial direct current stimulation over the left sensorimotor cortex does affect motor imagination, sensorimotor BCI performance, and sensorimotor rhythm power. We find that anodal stimulation does decrease the time to hit, particularly for right-hand trials, which is interesting, and I think warrants further investigation. Also see that cathode stimulation actually reduces or potentially does not allow this increase that happens with the sham and anode stimulation and alpha power. So these are things to consider when combining transcranial direct current stimulation and sensorimotor BCIs going forward in the future. So with that, I just wanted to thank a couple of other lab members as well as funding sources, and I'm open to, I think, a minute or two of questions.
Were all your subjects right-handed, or did you have any left-handed subjects?
Yeah, so we 26 of the 29 were right-handed, 3 were left-handed, and they were evenly divided between the 3 other groups. We didn't change the stimulation side based on the handedness, though that's something that we're looking at doing in the future, looking at more subject-specific stimulation and trying to parse that part of it out. Yeah, thanks.